Okay, so I'm going to walk through how you're going to design a state machine, starting from concept all the way to implemented circuit. So let's start by saying that I want to design a state machine that detects the sequence 101. So it's going to have a continuous bit stream coming in, and I want to output a signal whenever I see 101. So we start by drawing a state diagram. So the state diagram, I'm always going to start in some state 0. In a lot of these, you'll see me call it like idle or something, but let's start with state 0. So the way I would recommend in sequence detectors is always to start out by drawing the sequence that you want to detect and fill in the rest of what happens. So I need 3 sequences. I'm detecting a number of 3, so I probably need 3 states. I may need a 4th if I'm designing a more state machine instead of a mealy, but I'm going to start off with a mealy. Okay. So if I get a 1, I move to the next state. I get a 0, I move to the next state. That's the easy one. Now, if I didn't want to worry about overlapping sequences, I could just immediately say 1, and I'm good. But let's say I want to detect any sequence of 101. That means I don't want to start over just because I got that 1. So if I go 1, 0, 1, well, I've got a 1. So instead of being an idle, I really want to be back here. But I want an output of Z to be high. So 1, 0, 1, and we've detected Z. Now, I could go through explicitly on each one of these and say 0, no output, 1, no output. That's fine. It's a little bit more work, and I don't expect it unless I explicitly call out for it. Okay, so now I've got my detection going. Let's fill in the rest. Well, if I'm in state 0, this is an easy one. I stay if I get a 0. In state 1, if I go 1, 0, I've moved on. If I do 1, 1, well, I stay put because I just got another 1. And this state is saying that I've detected 1, 1 in the sequence without it getting another 0. So we hang out. All right, so now I go 1, 0, 1, I've detected. What happens when I do 1, 0, and then 0? Well, I don't go back here because that says I just detected a 1. And I can't stay here because that I would have to have a 1 and then a 0, but I have 2 zeros in a row. So that is starting over. So that's my state machine diagram. That's where we really want to start. Now we want to move on next to the state table. So I've already drawn out what the tables look like, where you're always going to have a current state, next state, and any outputs that you might have. So I've kept this one simple so we can move forward. So first I need to assign numbers to my current states. And I will just call them 0, 0, 0, 1, and 1, 0. Sometimes your numbering will make a bigger difference than otherwise, and I'll kind of show that why the state numbering may make a difference in just a bit. Right now, we'll just pick this in order because I step through and it's kind of an obvious ordering. Then I need to start stepping through and see what is my next state. Well, if I'm in 0, state 0, and I get a 0, I stay put. Otherwise, I go to state 1. Same thing holds here is I stay put if I get a, oh, that's not quite true. If I get a 1, I stay put. And if I get a 0, I go to the next one. Once I'm in state 2, if I get a 1, I go backwards, right? 1, I go back to state 1. So if I do 1, I go back to 0, 1. And if I get a 0, then I want to jump to state 0. And then similar for my outputs, I'm going to get zeros in all cases except for where I'm in state 2 and I get a 1. So that's filled out the state table. The state tables really help us figure out where we're trying to go from here. And the next thing I need to do is the next state logic, is how do we make the decision? So let's think about what a state machine really looks like. Well, the fundamental of a state machine is it needs some memory, right? We need to remember what we're in, and that is always going to be with a DQ flip-flop. The output of this is our current state. Sorry, let me look at this really close, make sure you guys can actually read that. I may need to make this bigger. Okay. A big DQ flip-flop where the output is current state. That feeds back around to some combinational logic. We'll just put the C that also has an input, and we'll call that I. In this case, it's just a bit stream that we're looking at, and that fits through here. This node is next state. Now, it's not just a simple single DQ flip-flop. This one needs to be 2 bits wide, as does the next state, right? Because we need 2 bits to represent all of our states. Okay, so this combinational logic then, we could design it both for 2 bits at a time, but that's complicated. So let's design it for 1 bit at a time. So for our next state 0 bit, this guy, this column, right? This one or that one. We need to make the decision what it's going to be. And we can do that by simply writing out a K-map, where my inputs to the combinational logic are my current state bits, C1, C0, and my input I. So what this is saying is that if I were to be current state 0, 0, and my input is 0, 0, 0, my input is 0, then my bit 0, what I'm calling NS0, next state 0, is 0. But if my bit is 1, if my input is 1, then I get a 1. Similar for 0, 1, it's 0, 1. Now 1, 1, I don't have that state, so I can just say don't care. And then 1, 0 is 0 or 1. Well, that's a nice gate, right? Because that's just as simple saying, well, it's this whole region, which then we say what doesn't change? I. That's it. So that's really nice. So that's going to just be, let me walk through this, make sure that I do everything correct. I is 1, right? Great. I'm going to erase this so they have a little bit more room, but remember that this is really what we're building. We're having some combinational input to the memory. And then each clock cycle, we just update current state with next state. Okay, so then our next K-map this is going to be our next state 1. And it's going to have the same thing, C1, C0, and I. And it's going to say that, well, if we're in 0, 0, then we're 0 or 0. 0, 1, we're 1 or 0. Again, don't care. And then 1, 0, we're 0 or 0. Well, that's not a very complicated K-map, right? Because we have a 1, we could just circle that, but let's take advantage of the don't care. The only thing, what doesn't change is I. And C0. Okay, so this is your process. So you've now been able to create, well, hopefully you can, draw the state diagram, draw the state table, turn the state table into a K-map, and then hopefully we can turn a K-map into circuits, right? By looking at what doesn't change. Therefore, when we have that feedback from that combinational logic, depending what our current state is that feeds back around to the combinational logic and the input that comes into that, we have an output that decides what our next state should be. So that's really the heart of the next states. Now, you'll notice that these maps can get pretty complicated pretty quickly. I won't do that to you too much on an exam, but you could likely see something where the input, right, we might have two inputs, or it might have one input but require 3 bits for states. I will avoid pushing you past needing 4 inputs. So your inputs are going to come from the number, the inputs to your K-map, rather, are coming from the inputs to the circuit and the number of bits required for your state. For the exam purposes, I won't go over 4 on that. So, but be prepared to do 4 rather than just the 2 and 1.